Imagine you're building a machine learning model to predict whether a patient will develop heart disease based on thousands of medical records. Your engineering team trains a classifier and reports back with incredible news. The model has achieved a 99.4% accuracy rate. On paper, it looks ready to deploy, but an inspection of the dataset reveals a glaring structural issue. Out of 1,000 patients in the test data, 994 are perfectly healthy. Only 6 actually have the disease. The algorithm didn't actually learn to detect heart disease. It simply realized that it could maximize its score by blindly predicting healthy for every single patient it sees. It passes a flat accuracy check with flying colors, but for the 6 patients who desperately need an intervention, the system fails entirely. This scenario traps software teams every day. When transitioning from traditional programming to artificial intelligence, evaluating a product requires entirely new diagnostic tools. Relying on flat accuracy without investigating the mathematical distribution of your data guarantees a perfectly executed, entirely useless product. To prevent these blind spots, product managers must strictly separate what they want to achieve from how they measure the algorithm. First, you establish the business outcome. This is the desired real-world impact of the product, usually measured in financial savings, physical safety, or operational efficiency. Second, you define the model output. This is the technical evaluation metric engineers use to grade the algorithm itself. Looking at this table, focus on the utility power demand forecasting tool on the right. The business outcome is straightforward, lowering the cost and emissions rate per megawatt hour. To get there, the engineering team uses a continuous regression error metric to track the model's output. Compare that to the airline turbulence prediction tool on the left. The business outcome shifts to minimizing safety incidents. That requires a completely different technical output, specifically a classification error metric on a 1 to 5 scale. Leadership must define the real-world business outcome first. Only then can they select the specific mathematical output metric designed to support it. This diagram maps the standard modeling process. Notice the direct, cyclical link between Step 1, business understanding, and Step 5, evaluation. Your business goals dictate your evaluation parameters. If you select the wrong technical output metric, your engineering development team will perfectly optimize the entirely wrong problem. For models that predict continuous numbers, known as regression, evaluation means calculating the distance between the model's prediction and reality. This table displays case 1, using a metric called mean absolute error, or MAE. It measures the average magnitude of the model's mistakes, treating all errors proportionally. Here, a steady stream of minor errors yields an MAE of 1.4. The primary alternative is mean squared error, or MSE. Before averaging the mistakes, it squares them. In case 1, with only small variances, the MSE remains a low 2.2. But watch what happens in case 2 when a single massive outlier hits the dataset. Because MAE grows linearly, it remains at 1.4. But the squaring mechanism of MSE heavily penalizes the large error, and the metric spikes to 9.8. MSE mathematically amplifies a single outlier, whereas the MAE metric steadily accumulates the average without letting anomalies distort the big picture. This mathematical difference forces a strategic decision.
You must ask, can your specific product tolerate being slightly wrong every time? Or is a single massive error catastrophic to the user? Choosing between MSE and MAE dictates whether your AI ignores anomalies or aggressively panics over them. We can apply that same rigor to classification problems, like our failed heart disease predictor. This 2x2 grid is the confusion matrix. When flat accuracy masks the truth, this matrix breaks the model's guesses down into 4 distinct categories. Along one diagonal, we have true positives and true negatives. These represent the scenarios where the model's prediction successfully aligns with reality. Along the other diagonal, we have false positives and false negatives. These show the 2 distinctly different ways the model can fail the user. To diagnose a model trained on heavily imbalanced data, we rely on 2 specific metrics derived directly from this grid. First is recall. It asks, out of all the actual positive cases in reality, how many did our model successfully catch? Second is precision. It asks, out of all the cases the model predicted as positive, how many were actually real. Breaking accuracy down into precision and recall provides the diagnostic clarity required to see exactly how a model handles critical minority classes. A common misconception about these classifiers is that they naturally output strict binary answers. In reality, models don't produce ones and zeros. They output continuous probability scores, indicating their confidence that a data point belongs to a specific class. This distribution curve shows that to turn those fluid probabilities into a definitive prediction, a human must draw a line. We call this the probability threshold. If you raise the threshold, you demand higher confidence from the model. This decreases false positives, but naturally increases false negatives because the model becomes hesitant to label anything a positive. If you lower the threshold, you cast a wider net. The model will successfully catch every true case, but it will flood your system with false positives. By setting this threshold, the product manager is explicitly choosing the trade-off between precision and recall. The probability threshold is the exact point where an unopinionated algorithm bends to specific business constraints. This creates an evaluation challenge. How do you measure a model's true quality if its performance constantly changes depending on where you place the threshold? To evaluate the model holistically, regardless of human input, we use the Receiver Operating Characteristic, or ROC curve. This graph plots true positive rate against false positive rate. We calculate performance at every conceivable threshold, mapping all possible behaviors. A capable model bows sharply toward the top left corner. Random guessing plots a straight diagonal line. The ROC curve allows teams to verify the model's baseline intelligence before committing to a specific arbitrary product threshold. But the ROC curve has one critical blind spot. The math factors in true negatives. If you have an extreme class imbalance, like millions of healthy patients, those massive numbers will artificially inflate the model's apparent success. For these edge cases, we use a precision recall curve. Because it completely ignores true negatives, the PR curve strips away the noise of the majority class, forcing you to evaluate the model based entirely on predicting rare, critical events. Model evaluation is not a passive checklist. It is an active translation of business constraints into mathematics. Choosing the right metric